What's poppin', dogs? Mr. Allen here with some solving of trig functions with double angles. And yes, it is double the fun. All right, so solve for theta when theta is bounded between 0 and 2 pi and when it's unbounded. So those are two different answer formats. Your teacher may ask you for either one on a test. I got you on both. Let's get it started, all right? We got 2 sine of 2 theta equals root 3. We got options here. I could rewrite sine of 2 theta as 2 sine theta cosine theta, but now I'm bringing in another trig function that seems like it's going to be overcomplicated because I don't have anything to pair that cosine up with. So maybe we just solve this one as is and deal with the 2 theta in post, okay? So I'm going to divide by 2 here on both sides. And that's going to give me sine of 2 theta equals root 3 over 2. Now root 3 over 2 I can solve with that, right? That's normal. So we could solve for 2 theta here. I'd get 2 theta is going to be equal to, well, when does sine equal root 3 over 2? I'm going to draw my triangles here. I'm a triangle guy, but you can do it on the unit circle. That's going to be at pi over 3 because it's going to be root 3. That's 2. So pi over 3 here in the first quadrant, and it's going to be over here in the second quadrant as well, which is 2 pi. Oops, don't forget my 2. 2 pi over 3. Okay, but that's what 2 theta equals. And here's where like the tricky aspect of double angles comes in. We actually have to expand this domain out even further and get more coterminal angles. So I end up needing to add 2 pi to this, or 6 pi over 3. So then I get 7 pi over 3. And I do the same on this one, and I'll get 8 pi over 3. 8 pi over 3. But why? Okay, because I always got confused. I'm like, wait, when do I do this? Do I do it with the doubles or the halves? Let's talk about why real quick, guys, okay? And hopefully this will help it all stick. Right now I have 0 to 2 pi for theta, right? So what if I did, let's see, we got 0 is less than or equal to theta is less than 2 pi. Well, if I want to make this 2 theta, right, I would just multiply everything by 2. So I'd have 2 times 0 is less than or equal to 2 times theta is less than 2 times 2 pi. Well, this is still going to be 0. This is going to be 2 theta. This is going to be 4 pi. Oh, so my 2 theta has an expanded domain essentially to all the way to 4 pi here. So I end up doing 2 extra solutions, just another set of coterminal angles for any of my solutions that I have here. I just went coterminal for each one. And now we need to solve this thing for theta. So how do we do that? Well, 2 theta is equal to all this, right? What if I were to divide by 2 here? That would give me just theta, right? And if I divide by 2 on this one, and on this one, and on this one, and on this one, I'll get my answers. So we get pi over 6. We have 2 pi over 6. We'll simplify that in a sec. 7 pi over 6. And 8 pi over 6. So all my denominators here, when I divide by 2, all my denominators just double, right? So I'm going to simplify anything that I can. It's going to be pi over 6. Then we have pi over 3. Then we have 7 pi over 6. And we have 4 pi over 3. Cool. So that would be my bounded between 0 and 2 pi. And you can also see that these solutions are between 0 and 2 pi for theta now. Otherwise we'd be like, we wouldn't have these two. We'd only have these guys, and these ones would be missing. There's more solutions that can fit between 0 and 2 pi. All right, now unbounded. Okay, let's go unbounded on this one here. Well, let's see here. Pi over 6. Can I get to 7 pi over 6? That I would add pi for that, right? I would add pi to get there. 6 pi over 6 would get me from 1 pi over 6 to 7 pi over 6. And then if I added that again, I would end up with, what, 13 pi over 6, which would be in the same spot as this. So we can actually be a little bit fancy here. Okay, we'd be a little fancy, save ourselves some writing. So for the first one, I'm going to do pi over 6 plus pi n. That's one of my solutions. And then for the pi over 3, I can also add pi to get here, right? Because this is in the first quadrant, this is in the third quadrant. This one's also in the first, this one's also in the third. So I'm going to take pi over 3 and add pi n. And there we go. We got ourselves our unbounded solutions. It's beautiful, man. It's awesome. All right. You could have just done pi over 6 plus 2 pi n, pi over 3 plus 2 pi n, 7 pi over 6 plus 2 pi n, and 4 pi over 3 plus 2 pi n, and that totally works, okay? I like to do this when I can do it because it saves a little bit of writing, and I find it fun to think about because I'm a math teacher, okay? But there we go. Cool. We good? Nobody said they're not good. So I'm going to move on. Okay. All right, let's go. So now I've got sine of 2 theta minus sine of theta equals 0. Well, we could go, no, I can't. I can't even do what I just did here, right? I can't solve for that. So let's see if the manipulation this time actually does work. So let's use our 2 sine of theta, cosine theta, plug that in here, okay? So 2 sine theta, cosine theta minus sine theta equals 0. Can I work with that? I actually can. I can take out a sine here. So I'd have sine theta and then 2 cosine theta minus 1 equals 0. Nice. So I have what's called the zero product property, right? Got to be equal to 0 to use that. Okay, don't start falling into a trap of like, oh, it's like equal to 8 product property. No, it's the 0 product property. So I can set sine equal to 0 here. So sine of theta equals 0. And I can do the 2 cosine theta minus 1 equals 0. So this would be cosine of theta equals positive 1/2. All right, so let's deal with this one first. When is sine going to equal 0? Well, sine's going to equal 0 on our x-axis there. So at 0 and at pi. And for this one here, I'm going to get, let's see here, when's cosine equal to 1/2? That'd be in the first quadrant. Actually, it's in the same triangle. That's wonderful. It's right there for me. That was pi over 3. And then in the fourth quadrant, cosine is also positive, which would be 5 pi over 3. Okay, cool. So let's go to work, man. Let's go to work. Well, those would be my bounded ones, right? Between 0 and, I'll leave it like that, between 0 and 2 pi. But now I got to go unbounded. Actually, that's going to bother me. I'm just going to go through. Wee, boom. Okay. So now we got to go unbounded. Well, 0 to pi, I could do this as, let's see here, just pi n. If n was 0, I'd get 0. If n is 1, I'd get pi. If n is 2, I get 2 pi, which is the same spot as 0. So yeah, that works. That's cool. And then how about this one over here? Can I write it in a way that would work? Well, if I add 4 pi over 3, I'd get 5 pi over 3. But if I add 4 pi over again, I'd get to 9 pi over 3, which is not in the same spot as pi over 3. Let me draw that up real quick right here. So this is where these are. We're up here. This is pi over 3. And this is 5 pi over 3. So if I add 4 pi over 3, I'd get all the way around to here. And I think we could kind of see already that if I had that same amount, I'm gonna end up a little bit further, right? And so I'm not gonna land back on this guy. So really I'm gonna treat these as 2 individual ones. I'm gonna go with theta equals pi over 3 plus 2 pi n, and theta equals 5 pi over 3 plus 2 pi n. So this guy and these two here are my unbounded solutions right there. You could pair up this pi with these here, and then you can add pi to each one of those. But I don't know if all of us are going to really think to do, or sorry, 2 pi over 3 to that. But I don't think we're all going to think to do that to like bring in this guy over here. But you could do pi over 3 plus 2 pi over 3. That would land on pi, then on 5 pi over 3, then back on this one, and then you just have 0 plus 2 pi n. But there's a lot of different ways to write these things. I think this is probably the easiest way to go about it, and it is correct. All right, so there we go, guys. Hope you enjoy these. Double angles can be a lot of fun. Be careful, especially in this situation here, when you have to expand that like domain because you're solving for 2 theta, not the other. See you later.